Let me tell you something right away. There's one equation that explains every light switch you've ever flipped, every radio station, Wi-Fi signal, lightning bolt, X-ray, rainbow, and magnet stuck on your refrigerator. I don't mean sort of explains. I mean it really is the same thing, underneath. And I spent a good chunk of my life poking and prodding this thing, first as a confused student, later as a professor, and eventually in the quantum version that got me a trip to Stockholm. So I'm not guessing. I lived with this stuff. Now, I'm going to cheat a little. The textbooks say there are 4 Maxwell equations. That's true if you count the scribbles the mathematicians like to spread all over the blackboard. But what I want to show you is how it all collapses into one idea, one law of nature that runs the entire electrical show. You don't have to know calculus, you don't have to remember any Greek letters. If you can imagine fields like invisible arrows and charges like little grains of sand, you're in business. When I first met electromagnetism, I was a kid in Far Rockaway, fooling around with radios. I didn't know anything about Maxwell. I knew if you wound a coil and stuck a piece of iron in it, and you put a battery across it, something pulled, something clicked, you twist a knob, and suddenly music appears from Pittsburgh or somewhere. It was like magic, but it bothered me that I didn't know what was actually happening in the space between the antenna and the radio. There's nothing there, right? Just air. And yet something very real is going across that space. That bugged me. Later at MIT, I met Maxwell's equations in the standard way, written out neatly on the board, 4 lines of symbols. Everybody around me was memorizing them like a catechism. I thought, this is nuts. Nature is not 4 separate little rules. Nature doesn't come in chapters like a textbook. It had to be one story. I could feel there was a single thing hiding underneath the notation. My job, as I saw it, was to dig that out and see if I could explain it as if I were talking to my father at the kitchen table. Let me tell you what I eventually realized. The whole of classical electricity and magnetism is just this. Charges make and respond to a field, and the field makes and responds to itself. That's it. One entity, the electromagnetic field, and one equation that, in its fancy form, just says how that field changes in space and time. All the different gadgets and complications are just decorations on that simple idea. You wiggle charges here, something wiggles over there later. The field is the in-between that carries the influence. So let's start from absolute zero. Throw away all the stuff you kind of remember from school. Imagine you've never heard the word electricity. I put a tiny speck on the table, call it a charge. I put another speck a little distance away. You see the second one move. You say, all right, there's some mysterious action at a distance. This one is somehow pulling or pushing that one. You could try to live with this invisible hand reaching across space, but it always felt fishy to me. The better idea, Maxwell's idea, which I fell in love with, is to say, no, 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 there's something in between. The first charge changes the condition of the space around it. It fills the space with an electric field, little invisible arrows at every point in space that tell any other charge which way to go and how hard. The thing that pushes the second charge is not the first charge directly, it's the field at the second charge's location. The equation for that, in its simple form, is what they call Gauss's law. It just says if you add up how much the electric field arrows are sticking outward through an imaginary bubble around some region, that tells you how much charge is inside the bubble. More charge, more field lines leaving, less charge, fewer lines. That one law already explains an enormous amount. Why hair stands up on a dry day, why you get zapped when you shuffle on the rug and touch the doorknob, why a thundercloud can throw lightning at the ground. Now here's the interesting part. In that picture, the field is just as real as the charges. It's not bookkeeping, it's not math tricks. It has energy, it can store energy, it can move energy around. When I finally swallowed that the empty space itself can carry energy and momentum, something flipped in my head. I remember sitting in my office at Caltech, drawing these little arrows in space and thinking, my God, the world is not made of little billiard balls bumping into each other. It's made of these strange, continuous fields. The particles are almost an afterthought. Up to this point, everything is electrostatics. Nothing is moving. That's already a lot. But it doesn't explain motors, generators, radios, or magnets. So now we let things move. Take a charge and start pushing it along. Now you've got a current. Wire, battery, charges, crawling through the metal. What happens to the field? Maxwell's answer in modern notation is packed in another one of his equations, but I want you to see the idea. A moving charge makes something new, what we call a magnetic field. So you don't just get electric arrows pointing in or out from charges, you get another set of arrows, circling around the current, wrapping around the wire like rings around a stick. That's magnetism. You see this every time you pick up a refrigerator magnet. Those little domains inside the magnet are like zillions of tiny current loops. All the electrons are spinning and circulating in a coordinated way, and the combined effect is this magnetic field sticking out into space, which grabs onto the iron door. No mood, no personality, just the fields pushing and pulling on charges in the material. At first, when I learned this, I treated electricity and magnetism like two separate forces that got married by accident. Here's an electric field, here's a magnetic field, they're friends, okay, next to the wire, also not moving. In that situation, the net electric field sideways could be zero, and there's no magnetic field from the charges because nothing's moving, so the little test charge just sits there, minding its own business. Now imagine you hop on a magic skateboard and you ride along next to the wire at some speed in such a way that now, from your point of view, those positive charges in the wire are moving relative to you, or maybe the electrons are the ones moving, depending how we set it up. Relativity says lengths change, densities change. When you work it out carefully, and I did many times trying to get an intuitive feeling, you find that what looked like a pure electric situation in one frame now looks like a mixture of electric and magnetic in another. Or vice versa, what you call a magnetic force in the lab frame is just an electric force in a different frame, because the densities of charges change due to length contraction. So the magnetic field is not some independent, mysterious substance. It's just the electric field reorganized when you change your point of view in spacetime. Like looking at the same object from above or from the side. That's a twist that knocked me out. For a while I had thought we had two kinds of fields and four separate equations. It turned out the whole thing was much more unified. One electromagnetic field dancing around in spacetime, and what you call electric or magnetic just depends on how you're moving. Now, Maxwell did all this before Einstein. He didn't know about relativity that way. But buried inside his equations was the clue. When you take his four classical equations and you massage them a little bit, this is the part I used to love to do on the blackboard, you get a single type of equation, a wave equation for the fields. It says that if you disturb the electromagnetic field in one place by wiggling a charge, say, the disturbance doesn't stay put, it travels out as a wave. And the speed of that wave is a particular combination of two constants that come from measuring electricity and magnetism in the lab, the permittivity epsilon 0 and the permeability m0. You multiply them together, take the square root of the inverse, and you get a speed. When Maxwell did this, he found the speed was 300,000 kilometers per second. He looked at that number and realized it was the known speed of light. That's the holy Moses moment. Light is an electromagnetic wave. You turn a charge up and down fast enough, the field shakes loose from the source and runs off through space, self-sustaining. Electric field makes magnetic change. Magnetic change makes electric change. They chase each other across the universe. If you want the one equation in its slick modern form, it looks like this. Nu equals mu j, nu. That's the whole classical story in one line. Here, F is the electromagnetic field, electric and magnetic, packed together into one object. J is the current and charge, and the little squiggly, it just says how things change in space and time. Don't worry if the symbols make your eyes hurt. The content is the same idea we've been talking about. Charges and currents create and respond to the electromagnetic field. The field itself propagates influences at a finite speed. I remember the first time I wrote that compact equation on the blackboard for my students at Caltech. I told them this one thing, if you squeeze it hard enough, gives you everything in this thick textbook. The static fields, the magnets, the plane waves, radio antennas, waveguides, light bouncing off glass, everything. The trick was not to impress them with the symbols, but to get them to see the picture underneath. A field that lives in space. Charges that source it, waves that carry it. Now, here's another twist that made it even more fun for me. When you take Maxwell's equation seriously, you get this wave traveling at c. But Einstein comes along and says, look, that speed is the same for everyone, no matter how they're moving. Once you accept that, you're forced into special relativity. So electromagnetic theory, this one set of equations, doesn't just explain electricity and light. It basically drags you, kicking and screaming, into a new understanding of space and time. That's not a small thing. Before Maxwell, electricity, magnetism, and optics were three separate subjects: static shocks, magnets, and light. After Maxwell, it's one subject, the electromagnetic field. Then, after Einstein, even space and time are mixed into this picture. This is what I mean when I say one equation can control a huge chunk of physics. It's like discovering one combination that opens every safe in the bank. You see the practical side of this unification everywhere. A radio transmitter is just a machine that wiggles charges up and down in a metal rod. That wiggle sets up a changing electric field. That changing electric field creates a changing magnetic field. They propagate together as a wave. Far away, your little radio antenna is sitting there. The wave comes by. The fields push the electrons in the antenna back and forth. That motion gets turned into a current, which your radio turns into sound. There's no radio stuff different from light stuff. It's all the same electromagnetic dance, only the frequency changes. Wi-Fi, cell phones, microwave ovens, it's just Maxwell's wave equation with different knobs on the frequency dial. X-rays, gamma rays, same field, much higher frequency, much more energy. Infrared, same field, just slower wiggles. Even the warmth you feel from a fire across the room is electromagnetic radiation hitting your skin. You could spend a lifetime working on gadgets built out of that one idea. A lot of engineers did, and they never had to invent a new fundamental law for each device. When I got into quantum electrodynamics QED, I was basically taking Maxwell's wonderful classical equation and asking, what happens when you remember that matter and light also behave like particles? Now the waves in the field are made of quanta photons. The field is still there, but now it comes in lumps. The interaction between electrons and photons gets probabilistic and complicated. I drew my little diagrams, those silly squiggly pictures with lines and vertices to keep track of how particles exchange quanta of the electromagnetic field. We got all these fancy corrections that match experiments to 10 or 12 decimal places. But underneath all that quantum machinery, the object we're quantizing is still the same classical field that Maxwell wrote down. Same one equation, just upgraded to live in the quantum world. So the classical law of electricity and magnetism didn't get thrown out. It turned out to be the classical shadow of a deeper quantum law. To me, that's a sign we were really on to something fundamental. Nature is stubborn about reusing good ideas. Let me circle back to the field picture one more time, because if you really grab that, you've basically got it. Suppose I take a charge and I jiggle it up and down. I'm putting energy into the electromagnetic field. That energy goes flowing out in the form of waves. Far away, some other charge starts jiggling in response, maybe in your retina. That's how you see. In between, there's nothing you can point to, no particles flying like little bullets in the classical picture. There's just the field being non-zero, vibrating in space. The equation, the wave equation for the field, just tells you that the rate at which the field's value changes in time is related to how sharply it changes in space. That combination gives you a wave moving at a definite speed. You don't have to remember the exact form. It's like the equation for waves on a string or ripples on water, with constants that come from electric and magnetic measurements. The miracle is that when you solve it, you get not just any old speed but c, and not just any waves but the light in your room. At Caltech, I used to draw little cartoons for the students. Here's a plus charge, field lines radiating out. Now I move it to the side. Near the charge, the field has time to adjust quickly. Farther away, the field is still pointing like the charge was before. So there's this kink, this bent region that peels off and races outward. That's the radiation. No philosophy, no metaphysics, just a concrete picture of how a changing source sends information out through the field at finite speed. That's what the equation is saying. If you strip away the snotty notation, the one equation that explains all electricity is simply The electromagnetic field in space and time is determined by where the charges and currents are and how they move, and in turn, that field pushes on those charges and can propagate through empty space as waves at the speed of light. Everything else is technical detail. You can send Morse code with it or Netflix, it doesn't care. Now, why do I think this is so important that I'd sit here yapping to you about it instead of playing the bongos? Because it shows you something about how physics works at its best. You start with a messy pile of phenomena: static shocks, compasses, rainbows, sparks, power lines, heater coils, radio shows, polarized sunglasses. It looks like a junk drawer. Then somebody, Maxwell in this case, comes along and says, wait, I think this all fits one pattern. And he writes down equations that, at first glance, look more complicated than the mess you started with. But if you stare at them long enough, and you rewrite them in the right way, and you do a few experiments to determine the constants, you suddenly find out they predict things you never put in. Radio waves, for example, were not part of the original input from a few basic principles. When my students used to come into my office, terrified about the exams in electromagnetism, I'd ask them, what makes a magnetic field? They start reciting curl of B equals m0j plus m0 epsilon 0 dE divided by dt. I'd stop them and say, no, 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 in English, in your own words. Don't bullshit yourself. And if they could finally say, a magnetic field is what you see when charges are in motion and when electric fields are changing, I knew they were starting to get it. The equations, then, are just a precise way of saying that, good enough that you can calculate the voltage in a transformer or the pressure of radiation on a sail. So, what should you take away from all this? First, that all the gadgetry of modern life, the lights, the motors, the electronics, the communication systems, is riding on one deep, simple structure in nature: the electromagnetic field obeying Maxwell's equation. Second, that what look like different phenomena, electric force, magnetic force, light, are often just different faces of the same underlying thing. Once you've seen that trick here, you'll start looking for it elsewhere, in the unification of electric and weak forces, in the idea that space and time are one space-time, all that jazz. And third, maybe most important, is the attitude with which you approach these things. Don't be impressed by the symbols. Don't be hypnotized by big names. Ask, always, what is this really saying? What's the picture? Could I explain it to someone who didn't know the math? If you can't, you don't understand it yet. And that's fine, that's the fun part. The pleasure is in the struggle to get a clean, simple mental picture of what nature is doing. Nature is what it is. It doesn't care how many equations you write or how proud you are of them. What Maxwell did, and what I tried to do in my own way with QED, was to listen carefully to what nature was whispering in all those little electrical and optical experiments, and then write down, as honestly and simply as possible, the rule she seemed to be following. The wonder is not that we can do that. The wonder is that when we get it right, everything from a lightning storm to a laser pointer falls out of one line. So next time you turn on a light or tap a screen and something happens across the world, remember, you're playing with the same one field, obeying the same one law that Maxwell wrote down in the 19th century, that Einstein used to reshape space and time, and that I spent my life doodling on blackboards and napkins. It's not magic. It's better than magic. It's the universe behaving itself according to a simple rule that you can understand if you're willing to think a little and not fool yourself.